intermediate at the end. So you could have 11 people leaving that elevator if you need to, as long as you work out with 0 in the end. And the other nice thing is that for power law distributions, it's even more accurate. And the analysis for power law distributions is going to be, so we're probably not going to get too much of the analysis for this lecture today, that you just look at the guys which are hit by a heavy hitter. And there aren't that many of them, because for power laws the heavy hitters are very rare. And then you take the rest of the bins and you look at the probability that in the rest of the bins something bad's going to happen. And that probability is a lot lower. So, first of all, you can immediately see that the counts that we get are a low bound. Why? Because for each bin, we increment it whenever we see this item, but we might have incremented it otherwise. So therefore it's a low bound. And so therefore the minimum is fine. Now, the probability of incrementing a bin at random, right, is 1 over m, because we have m bins. I might have picked a random bin, so that's fine. So therefore in expectation, the total overestimate is going to be n over m. So what we've done now with those two simple lines is we already have a lower bound on our estimator. When we have we have the expectation of the upper bound. We have the expected value of the estimate. So now all we need is a tail bound that will guarantee that we don't deviate by too far. And once we have the tail bound, we're safe. So this should now actually look very familiar compared to what we've done before. Basically what we're going to do is we're going to make sure that we have the probability that something good happens has some reasonably large probability. It doesn't have to be ridiculously close to 1, but just really reasonably large. And then I'm going to amplify that probability by a corresponding, in this case, minimum operation. Well, in other cases, people might take the median. Okay. So the Gauss-Markov inequality, so that very first, very simple inequality tells me immediately that the probability of a deviation above the expected value, is going to be, so if I deviate by beyond n over m, it's going to be 1 over e. That's just simple Gauss-Markov. And we know that this is the expected value of this random variable here. So that's all fine. Now, if I want to make sure that the minimum is above that threshold, because that's basically the accuracy that I want, I need to basically I need to draw enough instances that at least one of them satisfies that bound. We know that for each individual random variable that probability is 1 over e. I need to make sure that if I draw d many of them, that things are fine. But of course the probability of not hitting the lower bound for all d guys is one minus e. So we have the deviation being, bounded by 1 over e. So the probability that all of those guys exceed is, of course, e to the minus d. Because each of those random variables has to be evil enough to be outside the interval. Right? So this is very straightforward. So there we have a logarithmic guarantee and a 1 over epsilon accuracy. Okay. So what can you use this for? One of the first examples where Muthu Krishnan, so he's and Graham Cormode, where they used it was at AT&T for heavy hitter finding in IP ranges. So there, okay, suppose this is a tree that's given by your IP ranges, and you basically build this count-min sketch, and you keep the top of the tree exact. So you might keep, maybe the equivalent of a class C subnet, so exact, or maybe, you take 16-bit or whatever you can exactly store up to here. In everything below, you just push into the sketch. Now, if you do that, and let's say we have this range here, going over here, affecting all these guys, I only really need to look up the sketches at the boundaries. And that's all I need in order to get high accuracy. Likewise, if I want to get heavy hitters and I have this tree, I only need to follow down, the nodes in the tree that are heavy. Because if I know that this guy isn't heavy, then I know these guys can't be heavy either. So this is a very simple lookup. And that mitigates some of the effects that while you might have high accuracy, as soon as you go invoking that sketch many, many times over and over again, of course, the union bound, it still helps you because it's only log number of times that you invoke the sketch, but at some point log of some number is still going to be something very large. And yeah, that's what I meant with the range query. So you get, if I am interested in that entire range, then I just need to look at the nodes on that cut of the tree. So I think there's not enough time to really look at the tail guarantees very much for the count-min sketch. We're going to do that next week, and then we'll get to that and counter braids and how we can actually parallelize things, load distribution, consistent hashing, and so on. So what you'll see there happening is that the strategies that I explained in the very first lecture on basically systemz related stuff, where we looked at consistent hashing and reliability, fault tolerance, it will bring these to bear on these statistics, and that will actually give us new stuff. It will give us new algorithms that haven't been around before. Okay, any questions? Okay, well then let's finish.